a lot of discussions since yesterday and today as well about lithium storage, thermal storage, and sometimes lead acid is left a little bit on the side. Sharif just mentioned that based on his experience in Nigeria, lead acid still represents 70% of the market. But of course, there is a lot of hype about lithium. Now, does this mean lead acid is completely out of the game and no longer competitive with lithium? Well, actually, this is the topic of the following presentation. With Ashish Saxena, who is the General Manager for Africa and Asia Pacific at Eastman Global. Ashish will actually tell us about tubular gel batteries, which are type of lead acid ones that have some very interesting aspects to consider when planning projects. Just a little bit of background about Ashish. So he's calling us from India today. He's in charge of Eastman Global, brings in 15 years experience as in general management and international business development, and he's been with Eastman for the past 7 years. He's really focused on deploying the brand and the products in different regions in Asia and in Africa, with some very specific and interesting products. So Ashish, thanks for joining us today, and thanks for sharing a little bit of insights about what your company has been working on and what kind of solutions people may expect from working with you.
Yeah, good afternoon, everyone, and thank you, John, for having me again. Should I be sharing the presentation I prepared, or?
Yes, I believe that will be the best way, so you can manage your own slides as you progress through your presentation. Yeah, it's coming up, and you can go in presentation mode just for ease of viewing.
I think, yeah, that should. Yeah, so actually, as you rightly said, there has been a lot of views in the market that basically projects the lithium-ion as the next generation of energy storage systems for solar off-grid, microgrid, mini-grid, or even containerized power solutions. Problem basically with it is that our main objective is to show to the end users, to the project installers, to the independent power producers who are basically into the energy storage system utilization, that both the technologies, the lead acid and the lithium systems, can coexist based upon their application and based upon the segment where they are being deployed. So as everyone would know, lead acid as compared to lithium is a well-proven technology. It has been around in the modern world since the past 100 years, probably even earlier than that, if you believe the historical reports. And typically, if you see in terms of market deployment, the majority of the conventional flooded lead acid batteries and even the flat plate AGMs or even the tubular technology type of batteries are still the dominant choice for energy storage systems across the developing nations in Southeast Asia, Middle East, and Africa. It's only the high-end segment, or maybe what you can say the crust, maybe the top 20-25% people who can afford to pay in excess of maybe $5,000 to $6,000 for a well high quality branded type of lithium-ion energy storage system, and the balance of the market that remains in the economy range of segment, where price of projects and microgrids or even mini grids for rural electrification projects, where price is a very important aspect that determines the success of the project and the electrification that it provides to the community. In this case, the lead acid batteries more or less outcompete the lithium even as on date. And what we basically are trying to project is the next generation of the lead acid type of battery, where the tubular plates are basically amalgamated with gelled electrolyte. This technology was originally developed by Sonnenschein, it's a company in Germany, sometime in the 1950s. And we are presently in the 5th generation of the tubular type of lead gel battery phase, wherein there has been significant improvements made in terms of, let's say, the alloy which goes in, the electrolyte which goes in, and the components which goes in, which essentially boosts up its net capacity, its kilowatt hour capacity discharge, its cycle life and service life. So so much to an extent that it negates the difference, the advantage that you have in terms of cycle life with most of the 2nd generation lithium type of batteries. What you would say repurposed type of lithium batteries, which I believe are flooding the African markets presently. Slide. So, especially if you compare the major advantage that you have with the tubular type of batteries, we'll come to the construction later on in the future slides. The advantage that you have is its extreme temperature tolerance. For example, lithium, as pretty much everyone would know, it's highly susceptible to temperature variation. It must have a fire control system. It must have a very extremely well-designed BMS, a battery management system, which must be in congruence to the battery itself. The algorithm must be in perfect match to ensure that the cutoff and the cut-on type of batteries for the lithium system is in sync with the battery itself. Any mismatch in the BMS and the lithium pack basically results in a thermal runaway. And there have been very extreme cases of it where what you would say repurposed lithium, which has made its way onto the off-grid energy projects in Africa or Southeast Asia, have resulted in very severe fires, resulting in loss of property and threat to life. So this is where the lead gel tubular type of batteries come in with their extreme temperature tolerances. As of now, they have been successfully deployed in countries like Canada, where under sub-zero operating temperatures, and in countries which are in sub-Saharan region like Burkina Faso and Mali, where average daily temperature ranges between 40 to 45 degrees and even up to 50 degrees. So essentially, what gives the tubular gel battery its advantage is its construction, as in what it does is basically it's 5 different aspects to it. First, there is the alloy composition, wherein there's a unique calcium-calcium alloy for positive and negative plate, along with the additive for corrosion resistance, and zinc for giving it extra maintenance-free characteristics, along with the paste formulation that allows it ultra-long shelf life. And the separators are basically advanced type of corrugated PVC silica that gives it better absorption of the electrolyte, resulting in a very high electrocell osmosity.
Ashish, allow me to interrupt you just for a moment. It seems you have exited presentation mode. If you could just reinitiate again, because some of the writing
sure.
is a bit short, is a bit small.
Is this, are you able to see this?
Yeah, click on presentation mode. There we go. Yeah. All right, perfect. Thank you.
Right. Sorry. So as I was saying, there are 5 aspects to it in the plate construction. We are presently in the 5th generation of the tubular type gel batteries. In layman terms, it's basically the electrolyte is a fusion of silica gel and special type of polymer separators, along with tubular plate construction ranging between 2.2 mm dia to 2.8 mm dia, depending upon the market warranty. And that basically allows it ultra deep discharge capacity with a significantly higher cycle life. So this basically will give an idea, rough idea about how the tubular gel type of batteries can outperform, or even in terms of economic aspect, can give investors a significant advantage. So tubular gel type of battery, being without any battery management system, is compatible with almost 99% of the inverters in the market today. You don't have to buy a special inverter just for it to be in sync with the lithium battery pack, like you have to do for lithium systems. And the battery can be discharged up to as per your requirement, as in the battery will not cut off at a lower state of charge or low voltage. It is a settable aspect in the inverters, and it is user modifiable. The major part of it being a product of the renewable energy segment. This product is basically almost 80 to 90% recyclable. Each and every component in a lead acid or a tubular gel type of battery, at the end of its service life, the disposal of the energy storage system is a very big issue that has to be done in an environmentally friendly way. In almost all the continents in the world, there is an established supply chain system that can handle the recycling of lead acid or conventional lead acid, or even tubular gel type of batteries, wherein the lead alloy is recycled, the polypropylene components are recycled, the PVC separators are recycled, the copper and the zinc or any other alloy metal inside can be recycled. The only waste part of it is the electrolyte, which can be disposed of very easily, as compared to a lithium system, where as of right now, the supply chain for handling the battery at its end of life, at the end of its service life, is still in its infancy stage. Very few countries as on date would have a fully functioning supply chain system to handle the recycling or disposing of lithium-ion battery packs safely as per the environment regulations. So this is something that the lead acid type of batteries offer an advantage in. And I'm pretty sure the next table basically gives a rough idea about in terms of comparison, in terms of what you can say, the energy density. The lithium ion, obviously, there's no comparing the performance aspects. By inherent design, the lithium is a made lithium, a branded battery will any day outperform in terms of cycle life. But the investment in a virgin lithium ion pack will be almost 8 to 10 times over a lead acid or a lead gel type of battery. So the cost aspect has to be basically taken into consideration here. As you can see from the third column, the third row, the initial cost in terms of, dollars per kilowatt hour, or you can say per ampere. The prices are based on market average. And as you can see, the lithium ion, this is a very rough, giving a rough idea for the amount of cycle life that the tubular gel battery offers at 80% DOD, and the investment upfront that you have to sink in. It's a clear advantage in that terms. And this basically narrows down the gap in terms of performance and cycle life or economic benefit, financial investment that you have to make in a off-grid or a microgrid power project, and can significantly be of use to rural electrification projects. And finally, yeah, in terms of, as I covered before, the comparison that you do for a lithium-ion and a lead-acid type of batteries in terms of recycling and environmental impact. There is as I said, there is a supply chain in existence as of now for lead-acid batteries, and that itself can give economic value in terms of the scrap value that you get in terms of selling the lead-acid batteries at the end of its service life. Can be sort of like a payback to your investment. So you earn even after from the battery, even after you have over with the service life. We're open for any questions in case.
Thank you very much, Ashish. I thought you were going to go a little bit longer over the last slides. But yes, I think the key message from that slide is that indeed there is like an intrinsic value when working with lead-based batteries, which is something that most people forget. Now, and maybe this is going to be my first question for you. Yes, of course, there is a residual value, but how easy is it actually to get it as a single user? You have a project on your rooftop, you have your batteries. You know there is value, but it's not like somebody is coming to knock at your door to ask if you have some lead batteries to sell. What would be your recommendation for people to get the most out of residual or end-of-life lead-acid based batteries?
So even in countries which are developing, let's say, for example, I would say Nigeria, or even in the West, or Senegal in the West, or Kenya or Tanzania in the East Africa, there are basically lead recyclers. What they do is they take spent lead acid batteries. They buy it in scrap in bulk from maybe, let's say, agglomerators who are basically into the recycling of such products for automotive or for e-mobility or even for solar type of batteries, which are lead acid based. What they do is they don't come to your home, but they do offer doorstep pickup for a certain amount of charge, which is adjusted in the final scrap value. They effectively replace the scrap battery with like a service product, replacement battery, or a new battery. In case they offer retail distribution, there are some channels for this also, and you are basically not responsible for, as an individual user. Suppose you're using it in your home. You don't have to do anything apart from just handing it over, to the pickup representative. Once it is in their custody, then what they do is they extract the lead, they extract the polypropylene, they extract the silica, or anything that can be recycled, and the waste products are disposed of safely by their regulations. So there are several channels, supply chain channels here. Sometimes even the local assemblers of automotive or e-mobility batteries offer such services. They are existing, they are there with a full-fledged backup and support channels. And this basically offers us a very strong advantage over lithium-ion, because I know for a fact there are no such channels for lithium-ion recycling, especially in Africa. Very few countries have it. Maybe I believe there's one in South Africa. I believe there's one in Namibia. I'm thinking. Apart from that, it's still in infancy stage.
Yes, we will host one of these companies working on lithium batteries recycling tomorrow for those of you who will join us. But yes, indeed, it's still a nascent side of the industry, and a lot still remains to be done on that front. And just as a follow-up question on this end of life question, what would you say like is a reasonable estimate of the value that people can expect from reselling their old lead acid batteries?
So let's say the cost of a new conventional flooded lead acid battery is roughly around maybe $160 for a 200 ampere. At the end of life, maybe after 8 to 10 years, you should be getting roughly 30 to 35% scrap value based upon its weight.
That is indeed a significant chunk of the original cost. Yeah, so good for people to remember and to make sure they get the value out of their equipment down the road. You just mentioned something about e-mobility companies. I know this was not part of your presentation, but Eastman is actually one of the leading company when it comes to supplying batteries for that segment, which is also closely related to our topic at AVSIA, which is solar energy. Can you tell us a little bit about that? Are the batteries that you are providing for the e-mobility sector similar to the ones that you have presented today? Are they different? And what kind of opportunities do you see there?
In India, the e-mobility sector basically refers to mass transportation, public transportation, for providing last mile connectivity between, let's say, public transportation modes like MRTS or metro trains and offices and homes. So they have a battery requirement which is very similar to the type of battery which is used here. Is very similar to the conventional flooded lead acid. What differs is the type of tubular plates that goes in and the alloy mixture. That gives it, it is like a hybrid traction battery. As in, it can be deployed in traction applications for, let's say, scissor lifts or golf carts or even the airport cleaning machines or floor cleaning machines based upon the dimensions and the battery bank that they have inside. What they do is basically give you 6 hours of driving range for e-mobility three-wheeler type of segments. And this is something that is very unique to Southeast Asia, like countries in the Indian subcontinent. This battery basically is quite the rage as of right now because of its advantage in powering such three-wheeler electric vehicles that can ferry maybe 5 to 6 people to at one go, ranging between 8 to 10 kilometers per trip. And it gives you, as I said, it gives you a range of up to 6-hour driving time. And so it basically operates between the key working office hours and opening and closing hours. And the construction design, everything is same. And again, the inherent advantage comes in that at the end of its life, it can still pay you back in terms of scrap value.
Very good, thank you. Coming back to the traditional CNI space and to our African focus, you had a very interesting slide there with a comparison between the tubular gel batteries and the lithium-ion and the different specs of each.
Right.
But would it be possible for you to translate this into costs, cost per kilowatt hour or cost of life cycle cost, whatever metric you are using, putting yourself in the shoes of somebody who is planning to put some storage on their system and trying to guide them to understand what are the real cost advantage benefits between the two technologies?
Yeah, sure. So referring to the third row again here, referring to a 12 volt 200 ampere tubular gel battery that basically translates to 2.4 kilowatt hour energy. And similarly for a VRLA lead acid type of battery, similar specs. Lithium ion, it is assumed that it is a 24 volt, uh, uh, 400 or 600 volt configuration, because it is in increments of 3.7 volt. In terms of actual usage, you would be basically investing around roughly 190 to $200 for a tubular gel battery, roughly 170 to $180 for a flat plate VRLA lead acid battery, and in excess of I'm assuming we're talking about like a LG Chem or maybe BYD, which are branded high quality type of lithium ion packs. This would cost anywhere around $3,500 to $5,500 for a 48 volt system. In such a case, if it is used on a daily basis of 50% DOT, the tubular the tubular gel battery is rated to last around 1800 to 2000 cycles at 80% DOT, as compared to 400 to 500 cycles for a VRLA lead acid, and around 5000, maybe 4500 to 5000 cycles for a lithium ion pack. In such a case, the amount of investment that you make in a lead gel battery basically gives you 1800 to, let's say, 2000 cycles. This basically translates to a cost per watt of roughly around 0.07 cents per watt, as compared to 0.35 to 0.37 cents per watt for a lithium ion pack. This is a very rough calculation. Obviously, I'm just taking assumptions here, but in that sense, the tubular lead gel battery gives you a clear advantage in the amount in the investment that you make, in the lower investment that you make, and the higher output that you get for the money you make. So it is like narrowing the gap between like a lithium ion pack and the conventional flooded type of battery.
Thank you. And just while we are staying on these slides, this is a question on my side out of pure curiosity. Tubular gel and VRLA are based on lead acid, and yet there is a significant jump in terms of cycles. How
Yes.
is this actually made possible?
This is made possible by three inherent differences. So let's talk about VRLA battery first. You would be very aware about this type of, it is like a sealed lead type of battery, which is a flat plate type of construction with liquid electrolyte inside. It is a conventional lead acid flooded type of battery, with the only advantage of being sealed and being maintenance free, having a valve release mechanism that allows it to vent any fuming that comes in. How the tubular gel basically outperforms it is in terms of the thickness of its plate construction. So the thickness of the tubular plate varies between 2.2 mm in dia in mm to 2.8 mm dia. That in itself means more lead alloy, more components inside that allows it to give you more higher cycle life. And the second aspect is the electrolyte, which is free flowing in VRLA type of battery, is locked in the form of gel inside tubular lead gel battery. This basically allows for arresting the fumigation and the loss of water during cycling. During cycling, any battery, lead acid battery heats up, which results in loss of electrolyte. What happens is within 1 to 1.5 years in a VRLA, the battery dries up completely because you cannot open it. But this does not happen in tubular gel battery because of the locking mechanism of being fused with silica gel inside. This is the reason it can very easily outperform any VRLA battery in the world by several times in terms of cycle life. And the third aspect is basically the addition of some proprietary additives in the lead oxide that allows it to have extra intercell osmosity that allows for more free-flowing ions between the cells, and that again assists in terms of boosting the cycle life and the service life.
Thank you very much. Very clear. I have one more question for you before we close this session. Question from John, very active. Thank you very much for all your questions, John. John is wondering, okay, so based on your calculations, you currently have an edge on lithium, but then again, lithium is expected to significantly reduce in costs in the near future, even though this may not necessarily be true right now, but generally, I mean, there's a consensus to say that this technology is following this downward cost curve. What about your solutions? Is there also room for improvement, both on technology side, but also on cost side?
Yes, John. So in this case, during this initial phase of my presentation, I had mentioned that the tubular gel type of battery, which is in production phase across the world right now, is the 5th generation since 1950. So there have been 5 stages of technical upgradations in the chemistry, in the physical construction, in the components that go inside. In the next coming 5 years, by 2027, we are expecting to have a fully functional lead gel battery, a tubular gel battery with components that include carbon foam and high surface carbon that basically boosts up the cycle life by almost 45 to 50%. So if we are claiming right now, my tubular gel battery is rated at 2,500 cycles at 50% DOD. This will go up to, by 2027, it is expected to go up to around 4,000 to 5,000 cycles, what lithium is at right now, with the addition of carbon foam and high surface carbon additives in the form of plate construction. So obviously it will keep progressing on. The objective is basically to keep the costs low and come up with technical advancements in the lead acid or lead gel type of technology batteries that close the gap between what lithium has to offer. I'm sure even by then lithium may even advance on to 10,000 plus cycles, but then it's a race. I mean, it's, you know, there are obviously upgradations to it in once in every 4 to 5 years. It is in testing phase right now, and we should be coming up with a product that has carbon additives. We already have launched it in India. We will be very shortly launching it in our global markets also. Our product with high surface carbon. Within the next 4 to 5 years, we should be catching up to what lithium has to offer as on date.
Thank you very much, Ashish, for this comprehensive presentation of a somewhat less known battery technology. There were quite a few questions about this, so I'm sure people will be follow up with you directly. And before we close for today, and